Hi, my name is Emmanuel Godin and I will present what ASN.1 is and how to use it. ASN.1 stands for Abstract Syntax Notation 1. It is a joint standard by the International Organization for Standardization, the International Electrotechnical Commission, and the International Telecommunication Union. For the sake of simplicity, I will always refer to the ITU standard recommendation, not the ISO or IEC ones. ASN.1 was originally used to describe data transmitted by telecommunication protocols. And the data types described in ASN.1 can be translated to an implementation language such as C or C++, or they can directly be used in other languages such as SDL for modeling and TTCN3 for testing. Now you might wonder who is using ASN.1? Well, you are actually using it every day without knowing it. It's everywhere, but it works so well, it is invincible. Let me give you a few examples. X509, the standard that defines the format of public key certificates used in many internet protocols, such as SSL, the basis for HTTPS, LDAP, the lightweight directory access protocol, the voice over IP H323 protocol, SNMP, the simple network management protocol, the 3G and 4G mobile standards are all using ASN.1. The main goal of ASN.1 is to fully describe the interface between two entities exchanging information. It first aims at describing the type of information that is exchanged in an abstract way. It might be a simple information such as a boolean or an integer, or a complex type made of structures, arrays, or strings. But when it comes to exchange information in practice via a radio interface or a serial interface, the sender and the receiver might not be running the same kind of processor architecture. One might be an ARM-based processor and the other an Intel-based processor. So the information to be exchanged must be serialized so that it is platform independent. That is what we call encoding and decoding. Encoding turns an abstract information into a series of bits. Decoding turns a series of bits into an abstract information. These two aspects are reflected in the organization of the recommendation. The standard is organized in two main parts. The first one, the X680 series, defines the syntax of the notation from basics to parameterization. The second one, the X690 series, describes all the encoding rules. So we will first focus on the notation itself and then go through some of the main encoding rules. A few words regarding the syntax of the notation. ASN.1 is case sensitive. Keywords are written in capital letters. A comment starts with a double dash and ends with the same or the end of the line. The underscore is forbidden in identifiers and keywords. The assignments are written with a double colon followed by the equal sign. There are three types of strings. The character string is defined with double quotes, the binary string with a simple quote and followed by a B, the hexadecimal string with a simple quote and followed by an H. Regarding the organization, the top level container that will contain all the declarations is called the module. In practice, the module and its containing file have the same name. The available basic types are Boolean, integer, enumerated, and real. Please note that these types are abstract and that they do not have any link with the target architecture. Therefore, an integer, by default, does not have any upper limit. Another interesting built-in type is the null one. This type models the absence of information. Here is a simple example. The automatic type is a Boolean that will indicate if the gear shift is automatic or not. The age of the car is an integer and the color can have three possible values: red, blue, or gray. For the real type, the classical notation 3.1416 can be used, or the one with the mantissa, the base, and the exponent. The real value is then the mantissa multiplied by the base with the exponent. All the types in this example are abstract. As I said before, an integer by default does not have any upper limit. For that reason, most of the basic types are restricted in real applications. To do so, a range of values is put after the type between parentheses. For example, you could say that the age of the car is comprised between 0 and 50. Another way to restrict the possible values is to define a value set. One could say that the age of the car does not need to be that precise and could be 0, meaning less than 5 years, or 5, or 10, and so on. Enumerated values can also be associated to numerical values. In the example here, red is 1, blue is 2, and gray is 3. This information will be very useful when it comes to encoding the information into a real string of bits. One last thing, it is possible to define a default value when declaring the type. When a variable of that type will be instantiated, it will always have a defined and valid value. Some more basic types are available to handle time. The date type return year, month, day. The time of day return hour, minutes, seconds. And the date time type with both of them separated by the letter T. This might become handy. Now let's have a look at some of the string types. The bit string, for example, as its name states, is a string of bits. A bit string value is written between quotes followed by the letter B. The octet string is a string of bytes, where a byte is 8 bits. An octet string value is written between quotes followed by the letter H. The IA5 string is a way to describe a string of the good old 7-bit characters. An IA5 string value is written between double quotes. The IA5 string includes control characters, while the visible string does not. There exist other predefined string-based types in ASN.1 that are not discussed here. Let's move now to the structured types: sequence, sequence of, set, set of, and choice. First, the sequence type. It is an ordered series of elements. It is similar to a C struct. In this example, the car sequence has 3 ordered elements: the brand, the color, and the age of the car. Some fields in the sequence can be optional. To indicate this, the optional keyword is put right after the type name of the field. From an abstract point of view, making a field optional is similar to leaving its value undefined. When encoding the type, the optional fields, if not defined, do not have to be encoded, and a lot of bandwidth is saved. A sequence of is very different from the sequence type, as it is an ordered series of elements of the same type. It is similar to an array. Here is an example where my cars is a sequence of car, and car is a sequence with different elements. The set is an unordered series of different elements, so the declaration and the usage is similar to the sequence type. The main impact will be when it comes to encoding the information. The set of is similar to the sequence of, except that the series is not ordered. In practice, these two types are not used anymore because their unordered aspect does not have much interest. The sequence and sequence of will do the same. The choice type describes possible exclusive alternatives, meaning the information could be of that type or that other type, but not both at the same time. This is similar to a C union. In this example, the transportation mean is exclusively a car, a train, or a plane. My trip will be done with a car, in this case, a 2-year-old red Peugeot. One word on one of the advanced types that might become handy. Whenever you need to refer to a globally unique identifier, such as a digital certificate for example, the object identifier type allows you to point to references in what is called the object identifier tree. This is a mechanism standardized by the ITUT in recommendation X660 and ISO to produce a unique and ambiguous persistent identifier. Just to get the idea, this is the path you would take to reference one of ITUT recommendations. We have seen how to describe abstract data. Now it is time to send the information to a remote entity. To do so, ASN.1 comes with a number of standardized ways to encode the information into a bit stream. You basically don't have to bother with that. You have tools that will do the work for you. And this is it. But I feel you're curious to have a feel of what this is about. Okay, let's have a look at the basic encoding rule, BER, the packed encoding rule, PER, the XML encoding rule, XER, and the encoding control notation, ECN, that allows to define your own encoding rules. First, the basic encoding rule. Its nickname is BER, and as a first information, here is its identifier in the registration tree we talked about with the object identifier. The encoding is based on a TLV format. TLV stands for type, length, value. That means the first information will be the type of the data, the second will be the length of the data, and the last part will be the value of the data. The value might also contain another level of TLV formatted data. The type is usually on 1 byte. It contains some information about its class, its form, and its tag. The first 2 bits define the class of the type. The class is a way to indicate if it is a standard type or an application-specific type. Then, the 5th bit indicates the form of the type. If it contains subtypes, it should be set to 1, otherwise it should be set to 0. Finally, the tag indicates which type it is. Here are a few classical values for the tag: 1 for Boolean, 2 for integer, 3 for bit string, and so on. With only 5 bits to identify the tag, there might not be enough possible values for your own types. So to extend it to several bytes, set the 5 bits to 1, and the tag value will be the union of the following bytes having bit 7 set to 1. Next information is the length of the data. The short form is used if the length can be expressed with 7 bits. In that case, bit 7 is set to 0, and the others are used to express the length. If not, bit 7 is set to 1, and the 7 bits left are used to express the length of the length in bytes. If that still does not suffice, then you can set all the bits to 0 to use the indefinite length, and then the data ends with 2 null bytes. The short and long length are indicated as primitive form in the tag, and the indefinite one is indicated as a constructed form. This might look a bit scary for basic encoding, but that was the set of the general rules. Let's look at some practical examples now. What about a simple type such as a Boolean? The class is universal, the form is primitive, and the tag is 1. So the first byte value is 1. The length is 1 as well, and the value is 0 for false and anything else for true. That is pretty straightforward, but requires 3 bytes to encode a single Boolean value. Let's look at a bit more complex example. A visible string type containing John as a value. Tag 1a tells it is a visible string, length of 4 characters, and the 4 characters. Let's try some structured data, a sequence. Let's declare a sequence called person with 2 fields, name, which is a visible string, and age, which is an integer. We will assign John to the name field and 42 to the age field. The resulting bit stream starts as follows. The form bit in the tag byte will indicate it is constructed, followed by the sequence type value. The total length is 9 bytes. The value is actually the type of the first field of the sequence, a visible string, so the tag value is 1A, followed by 4, the length of the data, and the data itself, JOHN. Then comes the second field of the sequence, an integer, tag value 2, data is 2A, and length is 1. Okay, this is enough for BR. Let's now have a look at the packed encoding rule, PER. The goal of PER is to minimize the amount of resulting bits. And the opposite of the basic encoding rule, which uses TLV as a systematic approach, the packed encoding rule is based on a preamble, length, and value where each field is optional. The information is encoded if needed. And when it is, the information is encoded in bits rather than in bytes. In practice, the type or the preamble is almost never encoded in PER. Therefore, a Boolean that requires 3 bytes with BER only requires 1 bit with PER. Because the encoding is bit-based, it is very compact, but at the same time, it is more difficult to analyze. So there are variants of the PER, an aligned version that aligns the encoding on bytes and an unaligned version that only deals with bits. Here are a few classical values for the preamble. 1 bit only is necessary for a Boolean and none for a null value. Now when it comes to enumerated, even if a value is set for each item, the principle is to count the number of possible values and to find the lowest number of bits necessary to encode the value. So for example, if 3 items are enumerated, then only 2 bits are necessary. Same principle with integers. Based on the range between the minimum value and the maximum value, the minimum number of bits is calculated. As you can see, the packed encoding rule is quite tricky, so we will stop here and you can look at the standard if you really want to dig into the gory details. Good luck to you. A quick word regarding the XML encoding rule. It is definitely the simplest one as it is readable by a human, but it is also the less efficient one because it is verbose. The basic principle is simple. The name of the ASN.1 type is translated to the XML tag, and that's it. Let's have a look at a simple example to illustrate this encoding rule. We will use the same sequence example we looked at a few minutes ago, with a visible string field called name and an integer field called age. The resulting XML has first a person tag, which is the name of the sequence, containing the name and the age subtags and their respective values. As you can see, it is very simple to read and write. Last but not least, the encoding control notation. If the existing standard encoding rules are not satisfactory, it is possible to define one of your own with this notation. You can either extend an existing encoding rule or make a new one from scratch. The files are organized in two: the encoding definition module that describes the encoding and the encoding link module that makes the link between the ASN.1 data types and the encoding classes in the encoding definition module. Note the classes name have the name of the type prefixed with a hash. Let's have a look at a simple example just to get a grasp of what it looks like. The myBool encoding is based on bool class. It basically says it will use 1 bit. The true value is 0 and the false value is 1. I will stop here because ECN would require a presentation on its own. Now that we are done with the encoding rules, let's have a look at what the ASN.1 tools are about. The ASN.1 description is translated to first a data type declaration in an implementation language. And second, some encoding and decoding functions. A typical usage would be to translate the ASN.1 types to C types, develop with variables of these C types, and when the variables are fully defined, call the encoders and decoders associated to these types. Now, there are languages that directly understand ASN.1. The declaration is imported, and voila! The types are available to declare a variable. This is the case for SDL, Specification and Description Language, a standard from the International Telecommunication Union, ITU. Initially meant to describe telecommunication protocol in an unambiguous way, it is now used in a lot of areas such as aerospace, defense, automotive, medical, and more. Its success comes from the fact that it is one of the rare languages based on events that has an action language and a semantic of execution. So the model is very precise and can be verified. Another language supporting ASN.1 is TTCN3, the Testing and Test Control Notation, version 3. As its name states, it is a dedicated testing language. Often used for conformance testing, it can also be used for any kind of testing. Last language supporting ASN.1 is Erlang. Erlang is a programming language used to build massively scalable soft real-time systems with requirements on high availability. Some of its users are in telecoms, banking, e-commerce, computer, telephony, and instant messaging. Here is an example of how that would work with SDL. The person type is declared in the ASN.1 file. The package containing the declaration is imported in the SDL model. A variable of the type person can be directly declared and manipulated in the SDL model. You can see in the example how the name and the age fields are accessed and assigned. More or less the same process for TTCN3. Import the ASN.1 declaration and declare a variable of the type person. This is it. Thank you for your attention. Now, if you want to try a bit of ASN.1 with SDL and TTCN3, please feel free to download our tool from our website, which is free for small projects.